Hi, so let's try and understand SN1 reaction today in an interesting way. And let's visualize what really happens during an SN1 reaction. So let's imagine this is the substrate, this yellow one is the leaving group, the carbon that has to be attacked by the incoming nucleophile, and these are three alkyl groups. Let's call this one R1, this one R2, and this one R3. And these droplets right here, they're deliberate. These droplets right here represent the solvent in which the reaction is happening, which is supposedly a polar protic solvent. So what could be a perfect polar protic solvent that we all know of? Water. So water it is. So these are representing the water molecules, which are the solvent molecules. And this beautiful thing right here is the incoming nucleophile. So what really happens during an SN1 reaction is the bond between this carbon and the leaving group breaks. Let's call it bromine. And when it breaks, both the electrons of the bond are taken by bromine. So it becomes a bromide ion. And this becomes a 3-degree carbocation. And this carbocation is planar, as we all know. It is sp2 hybridized, it is planar. So what we expect is that, okay, once the carbocation is formed and the leaving group is like, okay, tata, bye-bye, that's when the nucleophile gets to attack. And since this is a planar ion, so the nucleophile has a choice. Woohoo, I want to attack from this side, I'll attack from this side to make a tetrahedral molecule again. Or if I want to attack from this side, I'll attack from this side. And therefore, we expect a racemic mixture. But, the reality is very different from the expectation. Because when we are starting the reaction, we have mixed everything together, right? We have mixed the substrate, we have mixed it in a solvent, and the nucleophile is also present right there. So whenever the carbocation is formed and this bond breaks, in the opposite order, of course, first the bond breaks and then the carbocation is formed, this nucleophile is not going to wait for its turn that, okay, bro, have you left? Can I now attack? Okay. No. Right when the bond starts to dissociate and this nucleophile observes a partial positive charge on this one and sees it leaving, it tries and come closer to the carbocation with an intent to attack it, of course. So it wants to come close right then. So what happens during this process is, right after this bond breaks, it forms an intimate ion pair. This is stage 1. Right after the separation, and we get this carbocation. So this nucleophile expects that it's very cool and it's going to attack from this side or from this side because it's his choice. No, it's not. No. You don't have the choice here. Because this leaving group right here is an electron dense species and the incoming nucleophile is also an electron dense species. So right after their separation, when we get this intimate ion pair where the leaving group is sitting right beside it, and the nucleophile tries an attack from this side, the leaving group is like, hey bro, are you trying to pick up a fight? Because I can clearly see that I am also electron dense and you are also electron rich. So what do you expect? Am I going to allow you to go from here? Of course we are going to have repulsions. So you're not supposed to come from here. Go from the back side. And this nucleophile is like, okay, I don't want to pick up a fight. So let's just attack from this side and let's just form this molecule instead. So there is a higher chance for this nucleophile to attack from the back side. What did we expect? That it would have an equal probability to attack from either side. But this leaving group, this bad leaving group is not allowing the nucleophile to attack from this side. And what exactly could be the next stage? What happens in the next stage? Okay, this is the intimate pair stage. What happens in the next stage? In the next stage, these solvent molecules are like, okay, so you are a carbocation, you are an anion, we are polar molecules. Of course, we are going to surround you. We are going to get attracted by you. And therefore, these solvent molecules surround the newly formed carbocation as well as the leaving group in such a way that they come in between these two ions. And therefore, we get a solvent-separated ion pair. So if at this stage, the nucleophile tries an attack, wouldn't it be really excited that, okay, finally I might be able to attack from this side? But, the leaving group is still right here. It's like, no, I didn't vanish. I'm still pretty close to the carbocation. So go and attack from the back side. Don't you get it? And the poor nucleophile still has the chance to attack from the back side more because it doesn't want to face those repulsions. And what finally happens is the last stage is the completely separated ion pair, wherein this carbocation is well surrounded by the solvent molecules which try and stabilize it by ion dipole interaction, and this anion is also well stabilized so that it doesn't attack back. So now this nucleophile is like, okay, so bro, where were we? So I can attack from this side and I can attack from this side. So what did we realize in this case? That okay, theoretically what we see is in the first step, this bond breaks, the carbocation is formed and the leaving group leaves, and therefore we expect that the nucleophile can attack from either side since this carbocation is planar. But what we really see is that the inverted product is way more. There's no perfect racemization happening here. And that's because this separation, when they go away from each other, occurs in 3 different stages, wherein they form the intimate ion pair first, then they are solvent separated, and then they are far off from each other. So when they are far off from each other, that's when the nucleophile has the perfect tendency to attack from either side. That's when this has a choice. This has equal probability. But it's not gonna wait until this this alkyl group was a little funny here. So this is not gonna wait until this is completely gone off, right? It's gonna take up the first chance it gets. Because this is an X right now. So it's not gonna stop trying. It's just not gonna try right in his face. He's gonna try from this side. So that's what happens here. So whenever you see a question that includes an SN1 reaction, you see them asking which of the following will have maximum racemization. And that's a beautiful question because there are chances of getting more inversion product in each case. But where exactly would we get more racemization? Try and think about it. Pause the video and think. The more stable is the carbocation, the more easily it will form, the more easily it will get separated from this leaving group, and the more would be the chances for this nucleophile to attack from either side, and the more are the chances to get a racemic mixture. So whenever you see a question that asks you in which of the following cases would be the maximum racemization, all you have to think is in which of those cases would you get a really stable carbocation, like the most stable amongst all, because that would be the case where the carbocation would quickly form, this would be quickly separated because the solvent molecules would be surrounding it more, and there would be more chances for the attacking nucleophile to attack from either side, and the more would be the racemization. I hope you liked the video. I loved making it, and if you really did like it, please like the video. Please subscribe to my channel.